We are very happy to have Damian Mayorga here to tell us about how to approximate Calabi-Yau metrics with neural nets. So take it away.
Okay. Thank you, John and Cody, for putting this very nice series of talks, and thanks also for letting me speak here. This is based on work done in collaboration with Vishnu Yiyala and Challenger Mishra. And basically what we want to do here is to discuss one of the recent machine learning approaches that have been devised to obtain numerical approximation to Ricci flat Calabi-Yau metrics. In this work, instead of approximating the Kaehler potential, we approximate the metric directly by an array of neural networks. And we apply this approach to different Calabi-Yau manifolds, such as the quartic K3, some members of the Dwork family of quintics, and the Tian-Yau manifold. So basically, Calabi-Yaus appear whenever you want to compactify string theory back to 4 or 6 dimensions, and what you want to retain some remnant supersymmetry. So if one takes, for instance, the heterotic string, one compactifies on a Calabi-Yau threefold in order to get some effective field theory in 4 dimensions, and the hope is that some suitable compactification would lead to some of the features of our observable universe. So furthermore, the total parameter space of a Calabi-Yau threefold is basically described in terms of Kaehler and complex structure deformations. They are parameterized by 2 integer numbers, basically in the case of threefolds, h11 and h21. And it was soon realized that Calabi-Yaus come in mirror pairs. So basically there are 2 Calabi-Yaus that are related upon exchange of these 2 numbers. And this is basically the idea underlying mirror symmetry that has also very interesting applications just in pure mathematics. So besides having their own standing both in physics and mathematics, Calabi-Yaus have also made some space in popular culture, and people name some techno albums. Also, they sell lamps in the shape of Calabi-Yaus, and some people have been inspired by this to create comic strips about a superhero who turns into a Calabi-Yau in order to see the extra dimensions. So more formally speaking, a Calabi-Yau of complex dimension n, Calabi-Yaus are complex manifolds, is a Kaehler manifold endowed with a metric and a Kaehler form that satisfies one of some equivalent satisfies any of the following equivalent properties. It has vanishing first Chern class. It has a Kaehler metric that exhibits vanishing Ricci curvature. It's endowed with an over vanishing holomorphic M form, and has a Kaehler metric with local holonomy SUN. There are some other statements, and basically the work of Yau was to prove that all those properties are essentially equivalent. And they are relatively easy to construct. So the simplest case is to take a weighted projective space and cut the Calabi-Yau by a hypersurface of an adequate degree. So in the case of, if you take P3 and you cut a quartic polynomial on it, then you get a K3 surface. And in here, I'm presenting the Fermat quartic. Similarly, there is the Fermat quintic, which is basically obtained by cutting a quintic hypersurface in P4. And one can further deform this polynomial by 1 parameter psi and get an entire family known as the Dwork family. And basically this Calabi-Yau becomes singular anytime psi is a quintic root of unity. Furthermore, one can take products of projective spaces and then cut the Calabi-Yau as an intersection of various hypersurfaces. So in this case, this is the Tian-Yau manifold. It's basically cut out of the product of P3 times P3 by a cubic in the first, a cubic in the second, and a bilinear equation in both P3s. It's very interesting because it has Euler number minus 18. And then if you quotient this Calabi-Yau by a freely acting Z3 symmetry, you get something which has Euler number minus 6. And this is interesting for phenomenology, as in some cases, the Euler number is related to the number of families. So in this quotient, one should be able to get 3 families. And there are some other examples, such as the shown manifold, that is cut by 2 polynomials in P1 times P2 times P2, and it has analogous presentation in this product of many P2s and this P1. So even though they are very easy to construct, well, relatively easy to construct, to date we have no analytic expression for a Ricci flat Calabi-Yau metric, in particular for threefolds. For K3s, there have been some recent developments towards an analytic metric. But since there's no analytic expression, the way to go is to access this metric numerically. And since the early 2000s, there have been various efforts trying to approximate the metric numerically using various techniques. And more recently, also machine learning techniques have been applied for this endeavor. Since the Calabi-Yau is a Kaehler manifold, the Hermitian matrix can be matrix G can be derived from a Kaehler potential, and related to the Kaehler to the metric, there is the Kaehler form that can be straightforwardly constructed, and one can prove that the Ricci tensor is obtained from this expression. A simple metric that one can put on a Calabi-Yau is the Fubini-Studi metric. This is not Ricci flat, but it's basically inherited from the ambient space. So this is the expression of the metric in the ambient space, and then you can further restrict it to the hypersurface. An algorithmic way to approximate the Calabi-Yau metric is to consider Donaldson's algorithm. So basically, inspired by the Kaehler potential, one can consider that instead of just the coordinates in the ambient space, one can consider polynomials on the Calabi-Yau up to a certain degree. And then these H alpha beta are going to be coefficients, and S beta is the complex conjugate of these holomorphic polynomials, a base of holomorphic polynomials. And then the task here would be to obtain the best matrix H alpha beta such that we obtain a good approximation for a Ricci flat metric. So let's assume that you would take nk being the number of, the number of such polynomials up to degree k, and then we define this quantity, H alpha beta, basically from integration of these polynomials weighted by the term that enters the logarithm in the Kaehler potential. The volume is just computed from wedges of the holomorphic top form and its conjugate. And then you can do this iteratively. So you can, for instance, start this metric H alpha beta is Hermitian. So you could start, for instance, with the identity, do this at step 1 and obtain this H alpha beta here. Then for the second step, you take the inverse of this H alpha beta that you obtain here, and you go on until the metric basically stabilizes. So this is known as the balance metric at degree k. And basically, as you increase the degree of the polynomials, you're approaching the desired Kaehler potential for the Ricci flat metric that you're looking for. This approach, of course, takes into account the Kaehler potential, and we want to follow a slightly different avenue. So let me first tell you what machine learning paradigm we are going to use. So basically, we're considering artificial neural networks. They are arrays of artificial neurons that emulate the human brain. And here you have a real neuron. it basically receives some stimulus, and then depending on the decision it makes, it decides to fire or not. So here, the artificial neuron takes some inputs, I1 to IN, and basically weighting those inputs and adding a bias, it gives a certain response as an output. And basically this response can be parameterized by some nonlinear activation functions, and here there are some of them. So this is the sigmoid, the hyperbolic tangent, and ReLU. And basically you can arrange these neurons in layers, and this is how you produce a deep neural network that takes outputs from the previous one and gives you inputs for the next. So our goal is to approximate a Hermitian matrix using neural network outputs. And for that, there is a suitable decomposition. This is known as the LDL decomposition. And basically, you take D as a diagonal matrix and L a lower triangular matrix with ones in the diagonal. And of course, since you expect the metric to be Euclidean, you hope for the parameters in the diagonal to be all positive. And to do so, we have created this array of networks, AN1 and AN2, that take affine coordinates as inputs. The first neural network gives you these eigenvalues, E1 to En, and the second gives you the entries of the matrix L. You combine these two, and this is how you obtain the metric G. So as the eigenvalues have to be positive, we don't just take the bare outputs of this neural network that can be, in fact, negative, depending on the biases. But instead, we take exponentials of those values in such a way that we guarantee that they are indeed positive. And the outputs of the EN2 we take in such a way that we can arrange. So remember that here we have to, well, I mean, we're using PyTorch, and here we cannot input complex numbers directly, so we always take real and imaginary parts. So the outputs of the neural networks are also real. And basically, in order to construct the matrix L, we have to combine them into complex numbers. So in K3, for example, the neural network would have two output parameters here, and then we will combine them in such a way as to produce the matrix L. So, as I said, we have taken real and imaginary parts of the affine coordinates as inputs. The number of neurons in the internal layers of each neural network was kept fixed throughout our work. So this we didn't change depending on the Calabi-Yau we were considering, and we fixed it to 500 neurons in 3 internal layers. The input for the hypersurfaces is 2 times n plus 1, where n is the complex dimension of the Calabi-Yau under consideration, and then you get n real outputs that are the diagonal entries here, or n times n minus 1 entries that I use to generate the L matrix entries. So in all of the experiments, well, we kept the number of neurons fixed, as I mentioned. We work with different activation functions. We used logistic sigmoid, ReLU, and hyperbolic tangent. And these neural networks were implemented in PyTorch, as I mentioned, but the data was prepared in Mathematica. So the data that we need here is are basically points in the Calabi-Yau under consideration, and we don't really have output. So this is, so what we have to do here is to obtain a loss function that optimizes the parameters here as to give us, well, a metric that is close to the Ricci flat metric that we want. So we have to take some properties into account in order to obtain this loss function. So basically we want the metric to be flat, and then this quantity sigma here ensures that somehow as this J is related to the metric. So basically this is the determinant of the metric. And basically this quantity gets minimized whenever the determinant of the metric approaches omega wedge omega bar, which is the determinant of the Ricci flat metric. Furthermore, since we are not deriving the metric directly from the Kaehler potential, we have to ensure that the metric is scalar. And for that, we have constructed this loss. So basically, it computes the volume, but instead of using the differential that you would get from the holomorphic top form, we use the volume differential that you'd get directly from the determinant of the metric. And basically, here you measure how the metric deviates, how the Kaehler form deviates from being exact. And additionally, we have to ensure that over different patches, there is a matching of the corresponding metrics. So basically, again, here we integrate using the volume differential obtained from the metric approximation. And here, this basically measures the difference between the metric at one patch and the metric at the other at another patch up to Jacobians. And basically, this M and L parameterize the coordinates that are set. I mean, one is the affine coordinate, and the other is the dependent coordinate. So that the coordinate that we solve for using the polynomial equation that describes the Calabi-Yau. This is for the case of the hypersurfaces. So the total loss function is a weighted sum of these three losses. So basically here, this alpha sigma, alpha kappa, and alpha mu are parameters that are suitably chosen such that all the three different losses are adequately minimized. And then the next issue is point sampling. So we have to find points that are suitably distributed in the Calabi-Yaus. So basically here what we do is start selecting random points in this cube, and then use them. They are real here, and then we use them to build a complex vector in Cn+1 and discard those vectors that have a norm bigger than 1. Furthermore, we project the remaining ones, so those which are contained within a sphere, to the surface of that unitary sphere. And as points in the weighted in the projective space that we are considering, these rescaled B's are uniformly distributed with respect to this SUM+1 symmetry that is exhibited by the Fubini-Studi metric in the ambient space. And furthermore, we can use any two unitary B's to construct a line in this projective space. So basically here, we just consider a parameter lambda. And this is, of course, the line that we obtained. And the points in the hypersurface that we sample are basically the points in the line that lie at the intersection with the hypersurface equation equals to 0. So basically, here's a sketch of what it was done. So basically, you take these lines that are built from random points, and basically, if this is the quintic, what you'd get is 5 points for every line that you have. There is a slight modification for the Tian-Yau manifold, because here we have 3 equations, and we have to ensure that whatever sampling technique we are employing is actually giving us some points in the manifold. So since this is a product of P3 times P3, we sample points identically as we did before in this unitary sphere. But in one P3, we take a line, and in the other P3, we take a plane, such that we have enough parameters to solve for the 3 equations. And then the points that we sample here are the points that lie in the line and in the plane that satisfy the defining equations of the Tian-Yau. And of course, then this is a symmetry that we can take for some specific choices of the polynomials. We can now interchange points such that we take the plane in the first P3 and the line in the second, such that we ensure that the points that we get here as planes and lines are uniformly distributed with respect to the Fubini study in the product, are going to give us some reasonable distribution of points in the corresponding Calabi-Yau. As an example, we could think of sampling points in the torus. So basically, we can take the cubic in P2. And for the cubic in P2, we have 6 patches that are depicted here in one of those. So basically, in this presentation, we have taken the coordinate set 3 to be the affine coordinate. We set it to 1. The coordinate set 2 is solved out of this equation. And then everything is given in terms of the coordinate set 1 that's here. And then basically, there's, of course, a preferred patch for each of these points. And this is precisely what is shown here, these 6 different patches. And these are basically the sampling results that give the same number of points in each of the patches, and each color represents one of such patches. The next thing that we have to do is to integrate. And of course, as you see, the patches intersect over 0 measure sets. So basically, numerical integration amounts as just summing over points in the preferred patch. But recall that the sampling method that we have chosen provides points that are only uniformly distributed with respect to the Fubini study, not with respect to the Calabi-Yau metric, the Ricci flat Calabi-Yau metric. And then in order to get sensible numerical integrations, we have to weight those points by a prior in such a way that if I want to compute the integral of a given function, I should take the measure of the Fubini study, and then you get these quotients of differential volumes. This would be basically the weight. And then numerically, I'll basically be averaging over the total number of points. Oh, sorry, this should be 1n. This weight times the function evaluated at the corresponding, at each of the corresponding points, as you see here. So this is basically how the numerical integration for the loss functions was computed. So let me just present some results. So this is an experiment that we run for the K3. We were training and testing with roughly 2,000 points. And this is how the sigma measure evolves as one evolves in the number of epochs. So you see that on the test set, on the training set, basically what we are plotting here is the determinant of the metric compared to omega wedge, omega bar. So it fits a line, but it's not so good at generalizing. This is partly due because of the number of points is so small, but here you can already see that basically the hyperbolic tangent is the one that gives you probably the best results in terms of how the sigma errors decrease for both the test and the training sets. And furthermore, we know that these hypersurfaces keep some discrete symmetries. And here we were testing for one particular discrete symmetry that basically takes the coordinates and rescale them by quartic roots of 1. And this is a symmetry of the hypersurface. And therefore, we expect the metric at points that are related by this symmetry to be the same. So this is sort of an extent of symmetry learned in a way. So basically, we're taking points, and we're evaluating the metric obtained from the neural network at a given point, minus the metric at the point after acting with the symmetry. And this is for every epoch. And this we rescale by the value of the metric. Well, here, the determinant of the metric at the given point. So this is what we obtained. We saw that the tangent hyperbolic was the one exhibiting the best behavior in terms of training and testing errors. And you see that basically the extent of symmetry learned decreases by roughly 2 orders of magnitude as training evolves. As I was mentioning, there is not only the sigma measure that we have to take care of, but also this kappa measure that takes care of the Kaehlericity, and this mu measure that takes care of the matching of patches. And we see that basically all three decrease as the training evolves here in one experiment only where we run for 400 epochs. For the Fermat quintic, so this was also the Fermat quintic, but with 2000 points, sorry. For the Fermat quintic with a larger number of points, you see that now the test set starts exhibiting a better behavior. And indeed, this is good evidence that the neural networks that we constructed are indeed capable of generalizing for a larger number of points. And the last one I want to show you, the results, these are still preliminary results. Here we only worked with the sigma measure. We didn't consider the mu or the kappa measures in this case. And you see that in the test set, things seem to work relatively well, but it's not so good at generalizing. So here, what we're considering is to tweak the architecture a little bit, because also in the previous cases, all patches were basically equivalent, so all points could be described in any patch. But here, basically, we have 4 different classes of patches. So if we want to minimize also these kappa and sigma measures, we might have to use a neural network per each family of such patches. So basically, those are the results I wanted to show you. So we managed to approximate to a certain degree the Ricci flat metrics using neural networks approximation. But of course, even if we improve on the errors, there remains a question for interpretability. And the question is if we can deduce analytic expression, or we can use these results to deduce analytic expressions, or get hints on what the analytic expressions for these Calabi-Yau metrics are. Symmetry hints that what the best architecture, the best activation function could be, and maybe there is a chance for us to use symmetries for architecture selection, for instance, or to construct improved loss functions. And since there are symmetries in many Calabi-Yaus, one question that arises also is if we can develop an AI symmetry classifier. And last, we see that the structure of our approach basically is modular. So we are taking the same neural network to approximate different Calabi-Yau metrics also in different dimensions. So there is hope that this approach can be extended further to other Calabi-Yaus, such as complete direct intersections, for instance. And yeah, basically this is what I wanted to tell you. And thank you for your attention, and yeah, I'm open for questions.
Great. Thanks a lot, Damian, for your very nice talk. Let us all thank him with our clap emojis. So we'll wait for questions. If you have a question, just type I have a question in the chat. Cody has a question.
Hey, Damian, thanks for the very nice talk. I was curious about this layer to get positive definite eigenvalues where you pass through an exponential. Did you try any other functions that would give you positive eigenvalues, and did that affect the training in any meaningful way?
Yes. So for the exactly. So here we took the exponential. Partly because we also don't want these eigenvalues to be 0, otherwise the determinant of the metric becomes 0 as well. But we also considered simply squaring them.
Mhm.
And at least for the points under consideration, we didn't get zeros, luckily. But I mean, this is not completely guaranteed, right?
Right. Okay, got it. Thank you.
And Fabian?
Hey, Damian.
Hey, Fabian.
Maybe you said it, but I missed it. So in the case of the Picaring 2 example, how did you ensure that the metric learned by neural network is in the same Kaehler class as the one that you fixed by pulling back the Fubini study to compute the weights for the integration?
Well, this is not, so, I mean, we don't know the Kaehler class, that's true. But I don't think that this is crucial for sampling, because, so, I mean, the points are chosen in such a way that the weight takes basically Fubini study and Ricci flat only, no?
But the weights are computed with respect to the pullback of Fubini study in a given Kaehler class.
Yes, but so basically the weights do not involve the metric that we obtained, right?
No, but when you compute sigma, you compute it by integrating using the weights.
Exactly.
Yeah, and these you compute for a specific Kaehler class, these weights.
Yes. I mean, the ones you use basically from the explicit expression of the Fubini study, no? So yeah, as I said, so here we don't know what is the Kaehler class for the Tian-Yau. There is still some work to be done in that direction. But I don't think that this is affecting so I mean, I think that the sampling process still gives you a reasonable result for the sigma loss.
Okay, we can discuss in private, I think.
Okay.
And Yidi?
Thanks. So how hard is it to train those combinations of networks? Because it seems that there's some overtraining issues in some cases.
Yeah. So one of the issues here is that we were taking real inputs and real outputs. So in computing, so these Frobenius losses, there was some time involved in bringing things from complex to real and vice versa. As you see, mostly these issues of overfitting can be ameliorated as you increase the number of points, as you can see for the Fermat quintic. In this case, we have taken basically 500,000 points compared to the 2,000 we're taking for the K3.
Okay, thanks.
And in view of time, let's take one real quick question from Paul.
Yeah, hi Damian. Just quick question. So do you think, or where would you think is the main difficulty to generalize that for weighted projective ambient spaces?
Well, the Fubini study, for instance, you have to figure out. I mean, first of all, the issue of the Kaehler classes. No, if you are not working directly with a Kaehler potential, you have to figure out in which Kaehler class you're actually working. This is a problem that here you see at the level of the Tian-Yau, as Fabian was mentioning, but it's going to be there also for the case of weighted projective spaces.
Okay. Okay, thanks.
Mm-hmm.
Great. So with that, let us thank Damian again, their emojis.